Right, welcome back everybody. Today is June 29 and I decided to do another try hacking room. This one is more on network essentials. Um, oh, wrong one. The networking concepts, sorry. So this one essentially covers the ISO OSI model, TCP IP protocol. It looks like IP addressing, subnets, UDP, TCP, encapsulation, telnet, and of course just the ending of it. I decided to go with this room in particular because currently I'm studying for my Net Plus, so I figured it'd be either a good refresher or I might learn something new. Okay, so we're gonna start. Get my notepad ready. Just complete. Okay, we're gonna start with the OSI model. Before we start, we should note that the OSI model might initially seem complicated. Don't worry if you encounter cryptic acronyms, as we provide examples of the OSI model layers. We assure you that by the time you finish this module, this task will feel like a piece of cake. The Open System Interconnection Model is a conceptual model developed by the International Organization for Standardization that describes how communications should occur in a computer network. In other words, the OSI model defines a framework for computer network communications. Although this model is theoretical, it is vital to learn and understand as it helps grasp networking concepts on a deeper level. The OSI model is composed of 7 layers. We have the physical layer for layer 1, layer 2, data link, layer 3, network, layer 4, transport, layer 5, session, layer 6, presentation layer, and layer 7, the application layer. The numbering starts with the physical layer being layer 1, while the top layer of the application is layer 7. To help you remember the layers from from bottom to top, you can use a mnemonic such as please do not throw spinach beaks away. You can check the internet for other easy to remember acronyms if this helps you memorize them. Remembering the OSI model layers with their layers numbers is important, otherwise you will struggle to understand terms such as layer 3 switch or layer 7 firewall. So we're going to start with the physical layer. The physical layer deals with physical connection between devices. This includes the medium, such as a wire, and the definition of the binary digits 0 and 1. Data transmission can be via electrical, optical, or wireless signal. Consequently, we need data cables or antennas, depending on our physical medium. In addition to Ethernet cable shown in the illustration below, and optic fiber cable, examples of the physical layer medium can include Wi-Fi radio bands, the 2.4 GHz bands, and the 5 GHz band, and the 6 GHz band. Layer 2, the data link layer. The layer defines a medium to transmit our signal. Data link layer, layer 2, represents the protocol that enables data transfer between nodes on the same network segment. To put it into simpler terms, the data link layer describes an agreement between the different systems on the same network segment on how to communicate. A network segment refers to a group of network devices using a shared medium or channel for information transfer. For example, consider a company office with 10 computers connected to a network switch. That is a network segment. Examples of layer 2 include Ethernet, i.e. 802.3, Wi-Fi, 802.11. Ethernet and Wi-Fi addresses are 6 bytes. Their address is called a MAC address, where MAC stands for Media Access Control. They are usually expressed in hexadecimal format with a colon separating each two hexadecimal digits, 1 byte. The three leftmost bytes identify the vendor. Vendor who built the network interface, in this instance Intel. Unique address of the network interface. Oh, okay, so we have the hexadecimal broken down for us over here. We expect to see 2 MAC addresses in each frame in real network communication over Ethernet or Wi-Fi. The packet in the screenshot below shows the destination data, link address, which is the MAC address, highlighted in yellow, and then the source data link address, the MAC address is highlighted in blue. So there's destination, the yellow over here, and then the source. So I guess where it's going and where it's coming from. The remaining bits show the data being sent. Okay. We have the network layer. Data link layer focuses on sending data between 2 nodes on the same network segment. The network layer is concerned with sending data between different networks. In more technical terms, the network layer handles logical addressing and routing. finding a path to transfer the network packets between the diverse networks. In the data link layer, we give an example of one company office with 10 computers, where the data link layer is responsible for providing a connection between them. Let's say that this company has multiple offices distributed across various cities, countries, or even continents. The network layer is responsible for connecting different offices together. The network below shows that computer A and B are connected, although on different networks. You can also notice two paths connecting the two computers. The network layer will route the network packets through the path it deems better. Examples of the network layer include Internet Protocol, Internet Control Message Protocol, and Virtual Private Network. Protocols such as IPsec and SSL, TLS, VPN. Okay. Transport layer enables end-to-end communication running applications on different hosts. Your web browser is connected to TryHackMe web server over the transport layer, which can support various functions like flow control, segmentation, and error correction. Examples of layer 4 transmission control are TCP and UDP. You have the session layer, which is responsible for establishing, maintaining, and synchronizing communication between applications running on different hosts. Establishing a session means initiating communication between applications and negotiating the necessary parameters for the session. Data synchronization ensures that data is transmitted in the correct order and provides mechanisms for recovery in case of transmission failures. Examples of the session layer include NFS, Network File System, and RPC, Remote Procedure Call. Presentation layer. Presentation layer ensures that data is delivered in a form the application layer can understand. So layer 6 handles data encoding, compression, and encryption. Sorry. An example of encoding is character encoding, such as ASCII or Unicode. Various standards are used at the presentation layer. Consider the scenario where we want to send an image via email. First, we use the JPEG, GIF, and PNG to save our images. Furthermore, although hidden from the user by the email client, we use multi-purpose internet mail extensions to attach the file to our email. Multi-purpose internet mail extension encodes a binary file using 7-bit ASCII characters. Okay, we have layer 7, the application layer. The application layer provides network services directly to end user applications. Your web browser would use HTTP protocol to request a file, submit a form, or upload a file. The application layer is the top layer, and you might have encountered many of its protocols as used different applications. Examples of layer 7 protocols are HTTP, FTP, DNS, POP3, SMTP, and IMAP. Okay, so this kind of just goes over what gets covered. So in the layer 1, from bottom to top, we have the physical layer, which is electrical, optical, and wireless signals. Data 2 is the data link layer. It's reliable data transfer between adjacent nodes, so Ethernet or Wi-Fi. We have layer 3, the network layer, logical addressing between networks. We have transport layer, layer 4, end-to-end communication and data segmentation, so UDP, TCP. Layer 5 is establishing, maintaining, and synchronizing sessions. I think it was new file share, network file system, and remote procedure call. We have data encoding, encryption, and compression. Other examples of that would be Unicode, JPEG, PNG, MPEG. And then we have the application layer, which is providing services and interfaces to applications. HTTP, we have FTP, DNS, POP3, SMTP, and IMAP. So, which layer is responsible for end-to-end communication between running applications? Session layer. Oh, let's take the hint. End-to-end communication. 2 layers. It's 4. Okay, while that loads, which layer is responsible for routing packets to the proper network, to the network layer? In the OSI model, which layer is responsible for encoding the application data? Layer 6. Which layer is responsible for transferring data between hosts on the same network? think that's actually layer 5. Oh, wait, transport. Wait, what? Which layer is responsible for transferring data between hosts on the same network segment? Hmm, I put 5 and it didn't go. No. So it's not 5, it's not 7. 2? Interesting way of wording that question. Maybe I didn't understand it. Transferring data between hosts. Oh, I guess live data transfer. Fair enough. Okay, I'm gonna move on to the TCP IP model. So, from my understanding, what I remember, it's basically kind of like the OSI model, just a little bit more compressed, with it only having 4 parts of it. As we go through this, so apparently this was made by the Department of Defense. One of the strengths of this model is that it allows a network to continue to function as parts of it are out of service. For instance, due to military attack, this capability is possible in part due to the design of routing protocols to adapt as the network topology changes. Okay, so the TCP IP model only has 4, like I said. From top to bottom, we have the application layer, which present. Okay, so from the application layer to the OSI model essentially compares to layer 5, 6, and 7. They're grouped together. Okay. Transport layer is just layer 4, same thing. Internet layer is going to be layer 3, the network layer. The OSI model, yeah, see, right here. Link 2, link layer is layer 2. Double checking everything here, pretty much. And many modern networking textbooks show the TCP/IP model as 5 layers instead of 4. For example, in computer networking, a top-down approach, 8th edition, Kuros and Ross describes the following 5-layer internet protocol stack by including the physical layer. In the following tests, we will cover IP protocol from the internet layer and the UDP TCP from the transport layer. Which layer does HTTP belong in the TCP IP, which would be the application layer? How many layers of the OSI model does the application layer TCP model cover? 3, 5, 6, and 7. We have IP addresses and subnets. So I learned a bit about this as well. Okay, we'll go over this. So you might think of an address like 192.168.0.1 or something less common such as 172.16.159.243. In both cases, you're right, both of these are IP addresses, IPv4 to be specific. Every host on the network needs a unique identifier for other hosts to communicate with them. Without a unique identifier, the host cannot be found without ambiguity. When using the TCP/IP protocol suite, we need to assign an IP address for each device connected to the network. One analogy of an IP address is your home postal address. Your postal address allows you to receive letters and parcels from all over the world. Furthermore, you can identify your home without ambiguity. Otherwise, you cannot shop online. As you might know, we have IPv4 and IPv6. IPv4 is still the most common. Whether you come across a text mentioning IP without the version, we expect them to mean IPv4. So what is an IP address? It comprises of 4 octets, which is 32 bits, being 8 bits. An octet allows us to represent a decimal number between 0 and 255. An IP address is shown in the image below. So we have 4 octets, and the numbers range from 0 to 255 each. At the risk of oversimplifying things, the 0 and 255 are reserved for the network and broadcast addresses, respectively. In other words, 192.168.1.0 is the network address, while the 192.168.1.255 is a broadcast address. Sending to the broadcast address targets all the hosts on the network. With simple math, you can conclude that we cannot have more than 4 billion unique IPv4 addresses. If you're curious about the math, it is approximately 2 to the 32nd power because we have 32 bits. This number is approximate because we didn't consider network and broadcast addresses. Okay. Looking up your network configuration. You can look up your IP address on the ms window command line using the ipconfig on Linux, Unix-based system. You can use the ifconfig or IP address show, which can be typed as ipa.s in the terminal below, which show Windows config. Okay. The terminal output indicates the following: the host laptop IP address, which is right over here, 192.168.66.89. The subnet mask being 255.255.255.0. Broadcast address is 192.168.66.25. Okay, so here's just an example of them using IP.A.S to compare how it looks on a Linux machine. Okay. If you're wondering, a subnet mask of 255.255.255 can also be written as /24, means that the leftmost bits within the IP address do not change across the network, i.e. the subnet. In other words, the leftmost 3 octets are the same across the whole subnet, therefore we can expect to find the addresses that range from 192.168.66.1 to the same thing, but 254. Similar to what was mentioned before, 192.66.0 and 192.66.255 are the network broadcast addresses, respectively. So we have private addresses. As we're explaining IP addresses, it's useful to mention that for practical purposes, there are 2 types of IP addresses. We have a public and a private address. RFC, what's that? Request for comments? Okay. It's a publication in a series for the principal technical development and standards setting bodies for the Internet, most prominently the Internet Engineering Task Force. Okay, close. Is it stuck there? Okay, anyways, there we go. RFC 1918 defines the following 3 ranges of private IP addresses. So we have 10.0.0.0 all the way to 10.255.255.255. So 10/8. And then we have 172.16.00, and then it ranges to 172 to 31 to 55 to 55. Okay, then we have 192.168.00 to 192.168 to 55 to 55. Okay, it's a pretty good way to remember it since they're odd. It's why is that to the 12? Interesting. Okay. We presented earlier an analogy stating that a public IP address is like your home postal address. A private IP address is different. The original idea is that it cannot be reached or reach from the outside world. It is like an isolated city or a compound where all houses and apartments are numbered systematically and can easily exchange mail with each other, but not with the outside world. For a private IP address to access the internet, the router must have a public IP address and support network address translation. At this stage, let's not worry about that, and we'll revisit it later. Okay. We have routing. A router is like your local post office. You hand them the mail parcel, and then they will know how to deliver it. If we dig deeper, you might mail something to an address in another city or country. The post office will check the address and decide where to send it next. For example, if it's to leave the country, we expect one central office to handle all shipments abroad. In technical terms, a router forwards data packets to the proper network. Usually, a data packet passes through multiple routers before it reaches its final destination. Wow, I'm not sure why I'm so tired. Okay, so the router functions at layer 3, inspecting the IP address and forwarding the packet to the best network, so the packet gets closer to its destination. So we have an office user, we have a couple routers here, mobile user, and a web server. Which of the following is not a private address? I'm gonna go with, well, so the private addresses started with 192, this one with 10, so well, they kind of also kind of give it away here. 4969 147 197. Which of the following is not a valid private IP address? Okay. This goes over 255, so it can be that one. 683519. Yeah, IP addresses have to be from 0 to 255, so that kind of helps. Private addresses, I remember I said 192.168, and then for 10, it was 10.0.0.0.0 to 10.255.255.255, and 1.72 to 16. So 1.972.16, and then these are 0.0, and then 1.72 to 31, was it? It was 31. Okay. So now we have UDP and TCP. So from what I remember was that UDP, it's not as, I guess the word would be strict as TCP, where it sends as much as possible, and if you get it, you get it, and it doesn't mind missing out on some of the data that's sent. Usually it's used for, I guess you would say, VoIP, so voice over IP or videos. And TCP is Transmission Control Protocol, which is a lot more like everything has to be sent in the proper order for the data to be correct. So that's used for more like messages and emails, things of that nature. But let's go over it anyways. So we have the UDP, which allows us to reach a specific process on this target host. UDP is a simple connectionless protocol that operates at the transport layer. Layer 4, being connectionless, means that it does not need to establish a connection. UDP does not even provide a mechanism to know that a packet has been delivered. An IP address identifies the host. We need a mechanism to determine that sending and receiving process. This can be achieved using port numbers. A port number uses 2 octets, consequently it ranges between 1 and 65,535. Port 0 is reserved. The number 65535 is calculated by the expression 2 to the 16th power minus 1. I guess because computers count 0 as 1 as opposed to we count 0 as 0. In real life, example similar to UDP is standard mail service with no delivery confirmation. In other words, there is no guarantee that the UDP packet has been received successfully. Similar to the case of sending a parcel using mail with no confirmation of delivery. In the case of standard mail, it means a cheaper cost than the mail delivery option with the confirmation. In the case of UDP, it means better speed, better transfer protocol that provides confirmation. Okay. TCP is a connection-oriented transport protocol. It uses various mechanisms to ensure reliable data delivery sent by the different processes on the network host. Like UDP, it is a layer 4 protocol. Being connection oriented, it is required establishment of a TCP connection before any data can be sent. In TCP, each data octet has a sequence number. This makes it easy for the receiver to identify lost or duplicated packets. The receiver, on the other hand, acknowledges the reception of data with acknowledgement numbers specifying the last received octet. So we have the SYN, SYN-ACK, ACK. So SYN packet, client initiates the connection by sending SYN packet to the server. This packet contains the client's randomly chosen initial sequence number. The server responds to the SYN packet with a SYN-ACK packet, which adds the initial sequence number randomly chosen by the server. ACK, the three-way handshake is completed as the client sends an acknowledgement packet to acknowledge the reception of the SYN-ACK packet. Which protocol requires three-way handshake? What is the approximate number of port numbers in thousands? 65,000. So you have encapsulation. Okay. In this context, encapsulation refers to the process of every layer adding a header, and sometimes a trailer, to the received unit data and sending the encapsulated unit to the layer below. Encapsulation is an essential concept as it allows each layer to focus on its intended function. In the image below, we have the following 4 steps. You have the application data. It all starts when the user inputs the data they want to send into the application. For example, you write an email or instant message and hit the send button. The application formats this data and starts sending it according to the application protocol used, using the layer below it, the transfer layer. Transfer layer, such as TCP or UDP, adds the proper header information and creates the TCP segment or UDP datagram. This segment is sent to the layer below it, the network layer. Okay, so we see it kind of building up over here. We have the network layer. The internet layer adds an IP header. Oh, okay. IP header to the received TCP segment or UDP datagram. Then this IP packet is sent to the layer below it, to the data link layer. So the data link layer kind of just gets, I guess, like the IP address. Anyways, the Ethernet or Wi-Fi receives the IP packet as a proper header and trailer, creating a frame. We start with the application data. At the transfer layer, we add a TCP UDP header, create a TCP segment or UDP datagram. Again, at the network layer, we add the proper IP header to get an IP packet that can be routed over the internet. Finally, we add the appropriate trailer and okay, so I guess in the examples that they were using with the mail, I guess this would be the the application data would be like, I guess, the empty pack, like a box. The TCP UDP header would be like whatever content you want on it. I guess my analogy isn't working. But the way I see it is, this is the box, and then when you get to here, you get to the actual content that you want. Well, this is the actual content that you want. So you put it in a box, and then you give it um, an address to go to, and then you kind of just send it. But that's how I'm interpreting it. Okay, so we have the life of a packet. Based on his studies so far, we can explain a simplified version of the packet's life. Let's consider the scenario where you try to search for a room on TryHackMe. On the TryHackMe search page, you enter your search query and hit enter. The web browser, using HTTPS, prepares an HTTP request and pushes it to a layer below to the transport layer, which is over here. The TCP layer needs to establish a connection by a three-way handshake between your web browser and TryHackMe. After establishing the connection, it can send the HTTP request containing the search query. Each TCP segment created is sent to a layer below the internet layer, and then the IP layer adds a source IP address, so it would be your computer, and destination IP address, the IP address of the TryHackMe server. For this packet to reach the router, your laptop delivers it to the layer below, the link layer. Depending on the protocol, the link layer adds the proper link layer header and trailer, and the packet is sent to the router. The router removes the link layer, header, and trailer, inspects the IP destination among other fields, and routes the packet to each proper link. Each router repeats this process until it reaches the router, the target server. On a Wi-Fi, within what will an IP packet be encapsulated? Header? Let's get that for now. What do you call the UDP data unit that encapsulates the application data? No spell. What do you call the data that encapsulates the TCP? What's up here? Segment. Where's the Wi-Fi? Header and trailer IP packet? So yes. Within what will an IP packet be encapsulated? Why did it word it like that? Ray. Yes. Threw me off. Okay. So there's a machine here. We're gonna start that machine here. Okay. So we have two machines. Okay, so this room is Telnet. Wait for these to boot up in the meantime. Okay, so let's just read along for now. The Telnet teletype network protocol is a network protocol for remote terminal connection. In simple words, Telnet. The Telnet client allows you to connect and communicate with a remote system and issue text commands. Although initially it was used for remote administration, we can use Telnet to connect any server listening on a TCP port number. On the target virtual machine, different services are running. We will experiment with three of them. Echo server, which echoes everything you send it. By default, this is on port 7. You have the daytime server. This server listens on port 13 and replies with the current day and time. We have the web server. This server listens on port 80 by default and serves web pages. Before continuing, we should mention that the echo and daytime servers are considered security risks and should not be run. However, we started them explicitly to determine communication with the server using Telnet. In the terminal below, we connect to the target VM at the Echo server's TCP port number 7. Close the connection plus control. Just waiting for these things to load up a little bit. We have our IP address here. Our tag box here. So we have the machine using Telnet to the current address and port 7 right after and connected to it. Escape character is control one of the brackets. Okay, let's try that. Try the machine number is 10, 10.56.32. So it's a private IP. Then 7. So it just echoes it back everything. Okay, I'm gonna get out of there. That's not working. It's not letting me leave. Even though I'm pressing. Let's just close it anyways. Alright, so let's try that. Interesting that control bracket wouldn't let me close it. Oh, I guess because maybe I need to use a C character. But I did. Anyways. Okay. We will request a web page using Telnet. I have to connect to port 80. So we're gonna try once again Telnet. And it was 10.56 and then 32. And then port 80. Okay. We need to issue the command get /http has to be if it's skin sensitive. On that one. So let's see an example. We connected to it. Like I already connected to it. And I put so send me things. Let's see what it says. Okay. Use Telnet to connect to the web server. What is the name of the HTTP server? Let's see what happens if I open the link. Took a while. So it's gonna be right over here. The server is light PD, light TPD. 463 page here. I gotta look for a flag. It's usually it's in the page. Oh, that was loud. Anyways, let's just look for this flag. So let's go. There was another one actually, right? So yeah, let's try this one. Oh, it's a lot. spaces. I don't know what I'm looking for, so I'm just gonna control. Oh, this one. There either. HTML2. It's only one. Correct. It's only five. Yes, it's not there. Which is here. Yeah, here. Done. Which is HTML print. Again. Two meshes. Okay. Let's check the terminal again. Check this one, check this one. Let's try it again. I'm getting something different. I just realized that too, because they're getting an okay. I'm not getting an okay. I'm getting a bad request. Let's check 10.10, 5.6, 3.2, and telnet 10.10, 5.6, 3.2, 80. So let's try. Maybe it's because it was case sensitive. P. That one. Just 10. Okay. Yeah, so I definitely wasted my time. What did I do wrong last time? It was probably this. The probably was case sensitive. HTTP, that one. Yeah, it's just case sensitive. Okay, good to know. But we have our code right over here. I'm just gonna put it in chat master. And we're gonna conclude. Cover the TCP, IP model, the OSI model, comparing contrasting the two, converted IP addresses and subnets, briefly explaining routing. Telnet to talk to different servers, and then we can just move on to network essentials. But we're gonna wrap it up here, and I'll get back to it next time. Yes.